All right, so the goal of this project was to compare different incline planes on Cal Poly's campus, basically just to see if the force of friction changed and force normal changed as the angle of the railings, in this case, changed. So we wanted to see if you increase the vertical component of the railing and you would go down faster, if that would change the amount of friction and the amount of normal force and your final velocity. And so what we did was we had Eric sit on two different railings. One had a very tiny theta, and the other was a larger theta. And the one with the tiny theta, he sat on it and didn't go anywhere. So his vertical acceleration and his horizontal acceleration, or sorry, his perpendicular acceleration and his parallel acceleration were both 0. And so if that's the case, we know that the vector sum of the forces in the perpendicular direction equals mass times acceleration equals force normal minus the force normal minus the perpendicular component of gravity, which equals 0. So that means force normal equals the perpendicular component of gravity. And from the pictures that you will see in the video, the perpendicular force of gravity is basically equal just to the force of gravity. And so the same basically happens in the parallel direction too. If you look at the vector sum of the forces of the parallel forces, they equal mass times acceleration equals the force of gravity parallel to the inclined plane minus the force of friction equals 0. So here we have the force of friction equals the force of gravity parallel, and from the pictures again, we know that this is basically 1/10 the force of gravity. So now we know the forces of friction and the force normal. When we look at the inclined plane with the larger theta, there's actually an acceleration in the x direction. He's still in perpendicular equilibrium with the inclined plane, but he actually slides down the railing parallel to the railing. So when we look at the vector sum of the forces of the perpendicular forces, again, we have our force normal minus the perpendicular force of our gravity equals 0, which means our force normal equals the perpendicular force of gravity. And then from this photo, we know that the perpendicular force of gravity is basically 4/5 the force of gravity. And then when we look at the vector sum of the forces in the parallel direction equals mass times acceleration equals the parallel force of gravity going that way minus the force of friction in the opposite direction. And so when we solve for this acceleration, we can plug in what we know. We know force of friction equals mu times force normal. We also know that force normal is 4/5 the force of gravity, so we can plug all of that in right here, and this is our force of friction. It's 4/5 the coefficient of friction times the force of gravity. And then we divide all of this by our mass to get acceleration, and then we run into a problem. We don't know what the acceleration is, and we don't know what this coefficient of friction is. And so we have to look at this through an energy lens. And we see that we start out with potential energy, and it goes to kinetic energy. And the only forces that give Eric kinetic energy as he goes down the inclined plane are the forces that are parallel to the inclined plane. So that's only the parallel force of gravity and the force of friction. So if we go up here, we know our potential energy is equal to the work done by the parallel force of gravity minus the work done by the force of friction, which is also parallel to the plane. And so when we solve for acceleration here, we get acceleration equals 4.1 meters per second squared plus 8 mu meters per second squared. And when we plug that back down to this equation, we get mu equals 0.05, which is a really tiny coefficient of friction. And then so when we solve for acceleration, we get 2.93 meters per second squared. So now we have the acceleration that we wanted to compare at the beginning of the video. And so now we can actually look at the forces themselves. And we expected to see a lower normal force and a lower force of friction with the inclined plane with the higher angle of or the higher theta. Because if you think about it, if you're sitting on something and it gets closer and closer to vertical, you're basically, once it's vertical, falling at the force of gravity. So we would assume that as this angle increases, your acceleration would increase and your force normal would decrease because it's harder to sit directly on it as opposed to something that's just flat. And so here we see, in the instance with the smaller angle, we have a much higher normal force than we did in this example with the larger theta and a larger vertical component. Meaning, and then we can see that the force of friction in the smaller one, the almost horizontal railing, is 70 newtons, and then it's much less in the instance where we have that larger vertical component. So our predictions were right. We were expecting this to happen. We're expecting there to be less friction and we were expecting a smaller normal force and therefore a smaller force of friction when the inclined plane was steeper. And we can look at this through the energy lens again. When we have the smaller angle, we know that our potential energy goes to kinetic energy plus the work of friction. And we know that in the smaller case, he's not moving anywhere. Both velocity and acceleration are zero. So if velocity is zero, kinetic energy is 0 joules, and we know that potential energy is equal to our work done by friction because the friction is keeping him stationary. And we know that if, in this case, he was on this inclined plane and there was no friction, he would accelerate and it would be tiny because it's almost horizontal. But again, he'd actually be able to move because there wouldn't be any friction here, and that would allow him to slide down the inclined plane. If we look at energy of the railing with a larger vertical component, we know that we have potential energy goes to kinetic energy plus the work of friction. And in this case, this is greater than 0. And the work of friction is 61.6 joules, which is much less than the 560 joules we calculated up there. And so when you solve for our final velocity, we get 4 meters per second. And when you solve for acceleration, like we did back here, you'd recall that that's 2.93 meters per second squared. And so we wanted to compare this and see if that was the actual acceleration and velocity we could see in the video using kinematics.
Go.
And so when we look at the video, we calculate a final velocity of 4.8 meters per second, which is close to our 4 meters per second, calculated through the energy lens. And we get an acceleration of 3.2 meters per second squared, which is also extremely close to the acceleration we calculated through dynamics and energy. And we did that just to basically double check our math and our logic. And so we can see through all of this that if you have an inclined plane that has a larger and larger vertical component, your normal force decreases and therefore your frictional force decreases, and so you have a higher acceleration and a higher velocity. Thanks for listening.